Hello everyone, welcome to our discussion of section 5.1 where we will be talking about finding the inverse of a function. Now, you're familiar with finding the inverse of a number, right? If you want to find the inverse of 2, you simply take the reciprocal of it, or 1/2. But how do we find the inverse of a function? And what do inverse functions have to do with the original function? In other words, how are they related? Because there's a strong connection between a function and its inverse, and we're going to look into that. Before that, as usual, please let me remind you to read through section 5.1 before you watch this video and before you attend class. Again, that doesn't have to take a long time. It should take, skimming through any section, most likely should take you 30 minutes to 45 minutes. It'll be very rare, unless it's a very lengthy section, that it might take you an hour or even an hour 15 minutes. It's very, very rare. But most likely, it'll take you 30 minutes to 45 minutes to do this. But it's very important that you do it before you watch the video and before you attend class. Then, as you attend the class or watch this video, please make note of any questions that you might have about the things that you see or hear me talk about. And also take note of the things that you think, oh, aha, I should remember that. Also take note of those types of information in your notebook. And then revisit that section of the textbook and go over all the problems that the book has solved without looking at those solutions. Redo the same thing with the video, with the problems that I have chosen for this video. And pause the video repeatedly and solve these problems before you see me work them out. And finally, and of course, complete all the homework by the due date. And finally, review the previous material. The review of the previous material should not take more than 30 minutes of your time each week. So if you do this regularly over the course of 16 weeks of a semester-long period, and if you spend half an hour reviewing the previous material, your mind will be very fresh on every topic that we talk about throughout the semester. But it just takes half an hour a week to do that. All right, having talked about that, we begin our discussion of inverse functions. So inverse functions, the way they're related to the main function is in twofold. One, it's a numerical relationship. We've talked about x and y quantities, right? So we've been talking about, as we've solved functions, we've talked about x and y, right? In the inverse function, the roles of y and x are reversed. So in the main function, whatever used to be x value becomes the y value in the inverse function. And whatever in the original function used to be the y value in the inverse function becomes the x value. And I've shown that in this example right here. So if the original, as it reads, if the original function corresponds to these points, -8, 5, 4, -2, -7, 1, these points, then the inverse function corresponds to these points. Compare them. Visually compare them. Notice how the roles of the x and y are switched in the inverse function and vice versa. Right? What used to be x is now y. What used to be y is now x. In this point, again, what used to be x is now y. What used to be y is now x. The same thing for these last pairs of points. So these are corresponding points where the roles of x and y are switched. Okay? I've shown that in this table of values. So this is, note the notation that I have used here. This is the original function, the table for the original function, and this table belongs to the inverse function, and we will talk about that notation in a minute. That's the notation we use. So if the original function, why not talk about it now, as a matter of fact, since it's right there on the screen. So if the original function is called f of x, then the inverse of that function is called f inverse of x. So this -1, I know it looks like a power, but it is not a power. It is just a name. It is just a symbolic mathematical name for the inverse of the function f. So if the original function was called h of x, then the inverse function will be called h inverse of x. If the original function was g of x, we will call the inverse function g inverse of x. Okay, so that's the notation. Now look at the compare once again, as before, as with these pairs of points, compare this table with that. Notice how the roles of x and y, right, the f of x is y, x and y are switched when we have the inverse function. So x was 10, 20, 30. Now for the inverse function, the y values, or if inverse functions values, are 10, 20, 30. And what used to be y is now x. Okay? So that's a numerical relationship between a function and its inverse. Okay? The inverse function and an original function also have a graphical connection. And I'm going to jump to the bottom of this page, and then I'll go back to the middle where we need to talk about all of this. But I want to talk about these two graphs as well. So notice that so f of x, if the f of x function is that, I'm going to highlight the original function. If that is the original function graph, then the inverse function is the other one. Is the image of the original function across this dashed line. So if you look at the mirror image of this highlighted function, then you will get this function, which is the inverse function. So the original function is the highlighted one, and the graph of the inverse function is the other one, which I didn't highlight, that one. How are they related? The inverse function graph is the mirror image of the original function graph across the y equals x line. The dashed line that you see is the y equals x line. That means as long as you're on that dashed line, all the x and y values are equal to each other. So you can easily list any possible point that is going to be on that line, on the dashed line. 1, 1, it's going to be on that dashed line. 2, 2, on that line. 5, 5, on that line. 100, 100, on that line. Why? Because for all those points, the y and x components are equal to each other. Okay? So that's the connection, graphical connection between a function and its inverse. The inverse function graph is the mirror image of the graph of the original function across the y equals x line. Okay? So the mirror is located at y equals x line. That's where the dashed line is. Okay? That's where the mirror is. Okay? So this one, again, we have the original function which I'm going to highlight. That's the graph of the original function. And the dashed line, of course, is once again y equals x line. That's the line on which all the points have coordinates that are equal to each other, right? 5, 5, -1, -1, -50, -50. X and y coordinates are equal to each other on that dashed line. But that dashed line y equals x is our mirror. That's where the mirror is located for an inverse function and a function to have an image on that mirror. Okay? So, once again, the inverse function graph is the mirror image of the graph of the original function across the y equals x line as the mirror. Okay? All right, so we talked about graphical connection between a function and its inverse, and we've talked about the numerical connection, right? Numerical connection between a function and its inverse. The other thing that we should know is that only one-to-one functions have an inverse. So I believe it was in this class where we talked about what constitutes a function and what doesn't. And it's very similar to that. One-to-one functions are functions where only one value of x is associated with one value of y. So how do we, in this course, we don't really look into that in a numerical sense that much, but graphically we do. So this is a horizontal line test is a way, because only one-to-one functions can have an inverse, so only the horizontal line test, the horizontal line test is a graphical way of finding out which functions are one-to-one and which functions are not one-to-one. So if a horizontal line, as the sentence reads on the screen there, if a horizontal line intersects the graph of a function only at one point, at any point along the graph, the function being tested is a one-to-one function. So if a horizontal line intersects the graph at more than one point, then the graph represents something that is not a function, not a one-to-one function. Okay, not a one-to-one function. It may be a function, but it's definitely not a one-to-one function. All right, so let's show a few examples of a one-to-one function. An application of the horizontal line test. So I'm going to do this on the piece of scratch paper, just so you have an idea what this is. So we know that the y equals x squared is a famous function, right? That's the quadratic function, y equals x squared. It is a function, and it is a famous function. But it fails the horizontal line test. If I draw a horizontal line, it'll intersect the graph at 2 points, right? So this is not, y equals x squared is not a one-to-one function. It is a function, but it's not a one-to-one function. Okay? In other words, in its current state, it does not have an inverse. But can we make this function so that it does have an inverse? Absolutely we can. How? Well, if we restrict the domain of the quadratic function, this quadratic function, to 0 to positive infinity, what are we going to get? Because the domain of this one, what is the domain of the current one? The domain is equal to minus infinity to infinity, right? That's the domain of what you see. But can we restrict the domain such that the function does have an inverse? Yes, we can. How? This is how. So we can say that we're going to strict or restrict the domain of this function to this domain for this one is equal to bracket 0 positive infinity. And this is still y equals x squared. This is still the same function. The same function, but this time notice the domain. The domain was restricted. Okay? Domain was restricted. And this is restricted domain. Why did we do this? Because now, if you run the horizontal line test, this function, the one with the restricted domain, for sure will pass the horizontal line test, right? So let's do that. So right there, if we have a horizontal line, it'll pass anywhere actually. You can draw a horizontal line where the horizontal line will pass the graph of this restricted function at only one point. So this function, which is the original function, now has an inverse over this domain, over this restricted domain, not over the full domain. Okay? You know, if you're going to be taking the Math 127 or trigonometry, in that class you will be doing this a great deal, because none of the trigonometric functions are one-to-one. But when you restrict their domain, for sure they are one-to-one. All of them can be made one-to-one when you restrict their domain. So just be aware of it, okay? Just because a function is not one-to-one in its original form, it doesn't mean that it will never have an inverse. You can make the function to have an inverse if you restrict the domain of that function over an interval such that the graph will pass the horizontal line test. Okay? So what are functions that are one-to-one? One very well-known one is the straight line graph, right? If you have a straight line such as that, if you have a graph like that, then for sure this function is always one-to-one, right? This is always, because if you draw a horizontal line anywhere, it'll only passes through that graph or crosses the graph of that linear function at one point. So any linear function is a one-to-one function. What is another example of a one-to-one function? The square root function, right? The basic square root function is one-to-one. So if you have, here's the graph of a basic square root function. It'll look like that, right? And this is y equals square root of x. Is it one-to-one? Yes, it'll pass the horizontal line test with flying colors right there. We can draw horizontal line anywhere and it'll pass the graph of the square root function at only one point. So the square root function is also a one-to-one function. Is the absolute value function one-to-one? Let's see. I'm going to draw the graph for that here. The basic absolute value function plots like this, like that. Is that a one-to-one function? And let me write this down. Y equals absolute value of x. That's the graph of the absolute value function. Is this a one-to-one function? No, right? If you draw a horizontal line, it'll pass the graph of the absolute value function at one point, at 2 points. So not a one-to-one function. Okay? There are lots of examples of functions that are one-to-one and lots of examples of functions that are not one-to-one. Okay? So that's basically the horizontal line test. Okay. And here in this note, I'm talking about the notation for the inverse function, which I mentioned earlier. If a function is called f of x, then its inverse is called f inverse of x. And that -1 is not a power, negative power. It's just part of a symbolic name for the inverse of a function f. And if the original function is called g of x, then its inverse is called g inverse of x. Okay? And we already talked about these graphs and the graphical connection between a function and its inverse. So, what about if I come along and claim that one function is the inverse of another function? How would you be able to prove or disprove my claim? That's the question before us next. So earlier, in the earlier sections, we learned about composite functions, right? Composite functions, as a reminder, this is why I ask you guys to spend half an hour a week, refresh your mind by going over the previous material. I hope you've been doing that, because now when I talk about composite functions, you'll remember everything about them. So with composite functions are functions such that they are created by placing or embedding one function inside another function. That's how composite functions are formed. If you claim, or if I claim, that two functions are inverses of each other, the way we can prove or disprove that claim is by taking composite function of the inverse function and the original function in both directions. So if we say that f and g, okay, suppose, let me add that. Suppose someone claims that f of x and g of x are inverses of each other. Okay? Then, how do we prove or disprove this? By taking the composite function in both directions. What do I mean by both directions? So we take the composite of f and g, and then g and f. Not one or the other, both. So it's critical that you take the composite function in both directions, this and that. Notice the first one is composite of f and g, and then g and f. If two functions are inverses of each other, then if you take the composite function in both directions, f of g and f and g and g and f, in both situations you must obtain x. Always x, always. If two functions are composites, are inverses of each other, when you take the composition of them in both directions, you must get x. The terms should cancel out, and you must simplify the result to x. If you're able to do that in both directions, this and that, that's why I highlighted this. So if you take the composition of the two functions in this direction and you get x, is that sufficient? No, that's what this box, that's why I boxed this. It's not sufficient. You must take the composite function in the other direction as well. G and f. Okay, so what are we doing all of this? The procedure for finding, so now that was the procedure to verify if two functions are inverses of each other or not. That was the procedure for that. Now, how do we find the inverse of a function to begin with? Right? If I put an exam question, this is often a popular exam question with me as well as the coordinators of this course, who design the final exam for this course. It's always a popular question. Find the inverse of this function. How do we find that? Well, first, we replace the function notation with y. We always knew they're the same thing, right? But the first thing we do, we replace that notation with y. Then we swap only the variables x and y. When I say only the variables x and y, that means don't swap their coefficients, just the variables. So if you have 2x equals y, you're not going to swap. So if you have, this is what that second rule is saying. So in the second step, so suppose you have y equals 2x plus 5, right? So we began with f of x equals 2x plus 5, right? We replaced, that was the first thing we did. The first thing we did was replace f of x with y. Then the second thing is swap only the variables x and y, not their coefficients. So the next step would mean I will simply say x equals 2y plus 5. Notice that the 2 stayed where it was. Only the variables got swapped. The numbers stayed where they are. Only the x and y swapped spots. Okay, that's what that second item means. The 2 stayed where it was, just the x was swapped and the y took its place. Okay, and then third, solve this new function for y. So if we solve this for y, we get x minus 5 equals 2y, and then y, when we solve for y, we need to isolate it, right? Is this y isolated? No. It's got a 2 right next to it, so we need to get rid of the 2. How do we do that? We divide both sides by 2. So we get y equals x minus 5 divided by 2. That's the third thing we do, okay? And number 4, in the final result, this is the final result. In the final result, replace y with the proper inverse function notation, which in this case is f inverse of x. Why? Because the original function was called f of x. So we replace y with that. F inverse of x equals x minus 5 over 2. And now we're done. Okay? I just used this scratch paper to show you what those steps are talking about. I think now they're clear. Okay? All right. So now let's begin going over these examples. The first one, it says if some original function f evaluated at 4 is equal to 11, determine the inverse of that function at 11. Can you answer this question? If you carefully read or watched this video when I talked about the first page, you should easily answer this question, right? We said that the function and inverse of it are connected numerically as well as graphically. Numerically, we said that the roles of the x and y are swapped. So if I know this inverse is this function is an inverse of that function, then what used to be y is now x, and what used to be x is now y, 4. So that's the answer. The x becomes y. By the same token, so can you answer this question then? If you pause the video, if you think about it, Can you answer this question before I write down the answer? What would you write down? You would write down, I hope, 30, right? If the inverse function at 30 equals 15, then the original function at 15 is equal to 30. So 30 as the independent variable value, or x, in the inverse function is equivalent or identical to the y value in the original function at 15. Okay? So numerically, the inverse function and function reverse the order of x and y components. What used to be x here becomes y here. What used to be y here becomes x here. Okay, I hope this is clear. So these two questions want to highlight the numerical connection between a function and its inverse. Okay, so the third problem, it says show that the two one-to-one functions, this and that, so they already tell us, don't worry about it. These two functions are one-to-one. They make that clear. It says show or prove, right, that these two are inverses of each other. Well, they say prove that, right? Prove this. So what did we say about how we can prove whether or not two functions are inverses of each other? What did we say? Do you remember? So, proving whether or not two functions are inverses of each other is based on our results from taking the composition function in both directions. Okay, if we end up with x, then the two functions f and g are inverses of each other. So let's do that here. Can you do that? If you've been reviewing, as I've asked you, you should have no trouble to find the composition of these two functions in both directions, if you've been reviewing. But if not, then that takes quite a bit of work. So if you have not been brushing off on the material, on the previous material, please pause the video, take a look back at the section or the video or your notes about the section where we talked about composite functions. I don't remember which section that was, but it shouldn't be that hard to find. Once you have your notes or once you have your book, you can just reference the table of contents. Brush up on that material, please. Just remind yourself about composite functions, then come back to this video. Okay, so I'm assuming you've done that and you know how to calculate the composite of functions. Okay, the way we do that here, let me take the composition of functions as f and g. So g gets embedded or placed inside f. Okay, so all of that gets replaced where x is, right? So bracket x minus 7 to 1/3 power cubed. Notice all of in f, all of the x is gone. Instead, I have, this is all g, right? But that's what we're calculating. We're calculating composition of f and g. All of g must be placed inside f, which is what I've done. Of course, plus 7. I didn't forget about that. Okay. So, as we know, we all know that by now, that mathematics is a cumulative subject. So it always works based off of not only the material that you just learned about, but the material you've learned in the previous sections, in the previous courses, and even back in high school or even middle school when you took some elementary geometry classes back then. And we've been using that, right? The area of a rectangle, the area of triangle, all those problems that we've done in the previous videos, they come to us from elementary geometry that we study in middle school or high school. So mathematics is cumulative. It always looks back at what you know previously. Okay, so we can't forget, the point of my making, we can't forget about what we covered previously. Okay, so now one of the things that we've covered in Math 96 or Math 95 is the properties of exponents, right? According to properties of exponents, if you have a to some power m raised to some power on the outside, right? This is when we talk about, I think by Math 96, we should have covered this material. This is part of what we call properties of exponents. If you've forgotten these and you're sitting at home watching this, please Google properties of exponents and brush up on that material. Make sure that you remember those properties. We know that if we have a power on the outside and a power on the inside, the two multiply each other. So ma is raised to m times n power. Okay? And if we have some base a to some power m times again to a times a to some other power, then because the bases are the same, we can add the powers, m plus n. Okay, these are two of the several, I think at least half a dozen or more I think, more properties of exponents, and you should know those. Okay, so following that, the properties of exponents, we have a power on the outside and a power on the inside. So we're going to multiply them, right? What do we end up with? We end up with x minus 7. 3 times 1/3 is 1, right? 3 times 1/3 is 1, plus this 7, okay? That power 1 means nothing, right? We can just write this without the parentheses now. So we get x minus 7 plus 7. And of course, the minus 7 and 7 add up to 0. We end up with x. So we took the composition function in this order, f and g, and we got x. So we've satisfied one of these conditions for proving whether or not two functions are inverses of each other. We've just shown this piece. Are we done? No. We need to show and this one. So we reverse the order of composition function and see if we still get x. This time composition of g and f. We did f and g. We didn't do g and f, right? So let's do that. So g, composition of g and f is equal to, this time f of x is the function that is being placed inside g, right? All of f must be placed inside g. Where can it go? Can it go here outside plus this? No, that would be combining functions. We're not combining functions. We're not adding or subtracting functions. We are taking the composite, finding the composition of two functions. The composition function means we need to replace x in g with all of f. Okay, let's do that. So instead of that x, I'm going to put that whole thing. So x cubed plus 7. There, I'm done now. Instead of x, we have x cubed plus 7. Why? Because that's the entire f that replaces x. Okay? Now we can complete the rest of this. Minus 7, close parenthesis, to 1/3 power, right? Pause the video, make sure you understand this step. This is the key step in this verification whether two functions are inverses of each other or not. Okay? Then, on the inside of this parentheses, 7 and negative 7 add up to 0. What do we end up with? We end up with x cubed on the outside, 1/3 power, right? Can we do something here? Yes. We have an outside power. We have an inside power. The rule of the exponents, properties of exponents indicate that we can multiply them. So when you do that, you end up with x to 1 power, right? 3 times 1/3 is 1, which is x again. So we took the composition of functions in both directions, f and g and f, and we ended up with x and x. Have we verified? Yes. We verified this condition, we verified this condition. Both of them led to x. Therefore, the initial functions f and g are inverses of each other. So f of x and g of x are inverses of each other. Okay? That's the result. Okay. Now, in question number 4, it says find the inverse of the one-to-one function. So that's when I did one example for you guys, just that one, on this scratch paper. Remember this, when I did that? We're going to be doing that. In this example, they're just asking us to find the inverse of this one-to-one function. And they're telling, and this is a linear function, so we know it must be one-to-one. But they tell us, hey, don't worry about it, this is a one-to-one function anyway. Okay, so this is a good point where you should pause the video, write down your solution, and then come back to the video. All right, I'm assuming that you've done that, and now you're back. Great. So the first thing we do, we're going to go through this list, right, on the same page. We're going to go through 1, 2, 3, 4 to find the inverse of this function. Okay. Okay. So first, let's replace f of x with y, right? I hope you did that in your own solution. And I hope next what you did was swap the place for x and y. So x equals 7y plus 4, right? The 7, the numbers state where they are. It's just x and y that got swapped. Now we have to solve for y. So x minus 4. If we're solving for y, we need to isolate y. So we need to get rid of the 4. We need to get rid of the 7. How do we get rid of this 4? We move it to the other side. When we do that, the positive becomes negative. On the other side, we are left with 7y. Okay, is y isolated yet? No, it's got a 7 next to it. How do we get rid of it? We divide both sides by 7. Right? So we have y equals x minus 4 divided by 7. Oops, so that's still not the final answer. The final answer is when we replace this y with the proper inverse function notation. The original function was called f of x, so the inverse must be called f inverse of x equals x minus 4 divided by 7. That's the final answer to that. Okay. All right, so number 5, it says find the inverse of the one-to-one function. Okay. So again, you can see examples numbers 5 and 6. Pause the video, please. Right there, right now it's the perfect time to pause the video, write down your solution on a piece of scratch paper for both of these problems, and then come back to the video. Okay? All right, so I'm assuming you're done with that, and now you have solutions for both of these problems. All right, so first we will replace f of x with y. Then we will swap x and y. Right? Now we have to solve for y. So first, multiply both sides by y minus 4. So y minus 4 times x equals y minus 4 times 9y over y minus 4. On the left, we have xy. We're going to distribute and simplify. Xy minus 4x equals, what about the right side? The right side, this and this cancel each other. We end up with 9y. Which variable are we solving for? Y, right? Not x. So, how many spots does the variable y appear in this equation? How many spots? 1? No. 2, right? 2. It appears here and it appears here. So because we're solving for y, and y is appearing in 2 spots, not 1, we need to put both terms that have y in them on one side and send anything that doesn't have y in it to the other side. So we have xy minus y equals 4x. And that's what I did. I put both terms that have y in them on the left. I put the minus 4x to the right side. So minus 4x, when I move it across the equality symbol, becomes positive 4x. Positive 9y, when I bring it to the left side, it becomes minus 9y. Okay? Okay, so now we're solving for y. But is y isolated? No. It's part of 2 terms. What do we do? What should we do now? What technique we've learned so far, or we've practiced it at least. You've probably known that technique before taking this course, but in this course so far, we've practiced with it many, many times. What technique is that can help us isolate y one more step? Do you remember what technique that is? Right? Y appears in 2 terms, not 1. So we have to factor y out. So factor y out, we get, what should I put in the parentheses here, such that when I multiply it by y, I get xy? Well, just x, right? Y times x is equal to xy, same thing. What should I put in the parentheses here as I factor y from both of these terms, such that when I multiply y by it, I get minus 9y? Well, minus 9, right? So distribute, factoring is the opposite of the distributive property. Redistribute y into both terms. What do you get? You get xy minus 9y. So the factoring we've done is correct, equaling the other side. Okay, so we're solving for y. Is y isolated yet? Not yet, but we're close. So what do I need to do to isolate y and therefore solve for it? Well, we need to get rid of the x minus 9, right? So divide both sides by x minus 9. And we end up with y equals, so x minus 9 and x minus 9 cancel, because this whole thing is being multiplied by y, so we can cancel that whole thing with this whole thing. Y equals 4x divided by x minus 9. Are we done? Almost, but not yet. What do we need to do? Just replace y with the appropriate function inverse function notation. We started with f of x, so we need to write f inverse of x equals 4x divided by x minus 9. And that's the inverse function. When we're done, we have more examples to come. When we're done with this, this practice of finding the inverse functions, I'm going to go to the computer and we're going to graph these so you can see the graphical connection between a function and its inverse. Okay? As we said earlier at the beginning of today's lesson, we said that the two, graphically speaking, are mirror image of each other across the y equals x line. We're going to go to the computer and actually plot these and see that behavior, okay? So for now, just make sure that you are able to obtain the inverse of a function. Okay, I'm assuming that you've also solved number 6. So I'm going to go ahead and find the inverse here. So the first thing is replacing f of x with y. Then I'm going to swap x and y. Right? And then let's multiply both sides. Let's clear the fraction by multiplying both sides by y plus 9. Like that. On the left, what do we have? We have xy distribute. X times y is xy. X times 9 is plus 9x equals, on the right, y plus 9 and y plus 9 cancel out. We end up with y minus 9. We're solving for y, right? Notice that y, once again, is appearing in two spots. So we need to put both terms that have y in them, which is the variable we're solving for, on one side. So we have xy on that side. I'm going to move this y to the left side of the equality. So it was positive on the right side. When I move it, it becomes minus y equals. This minus 9 is okay. When I move this minus 9, so minus 9 on that side is okay. I'm going to move this positive 9x to the other side. When I do that, this plus becomes negative. Okay? For sure, I'm sure you're noticing that we can factor out minus 9, right? We can do that later. But for now, let's focus on the left. We're solving for y, and y is appearing in two spots, not one. So how do we isolate y by itself from these two terms? We use the technique we just used for the previous example, right? We factor y out, right? What should I put here to multiply by y and get minus y? The minus is there already. What else should I put here? 1, right? Equals minus 9x. Is y isolated yet? No. It's got an x minus 1 next to it, so we need to divide both sides by x minus 1. Okay? On the right, on the left, these cancel out because they're being multiplied. Okay? If this was y plus x minus 1, I could not cancel them out. But y is being multiplied by x minus 1, so I can cancel them out. So we get y equals, let's factor that numerator, minus 9 times y plus x, right? Divided by x minus 1. Okay? And then one last thing is to replace this y with the proper inverse function notation. We started out with f, so we replace this with f inverse of x equals minus 9 times 1 plus x divided by x minus 1. Like that. Okay. All right, I hope this agrees with the answer that you have reached in your own, on your own paper. Next one is an interesting one. It's a square root function. We know these are one-to-one functions, right? Earlier we looked at the graph of the basic a square root function, right? Right there. The basic square root function has this form. And so we know these category of functions, the square root functions, are one-to-one. Okay, so let's find the inverse of that. If you haven't done so already, please pause the video, find the inverse of that function, find the inverse of that function, and then come back to the video after that. All right, I'm assuming you've done that. So let's proceed. We have y equals square root of 3x minus 5. Then let's swap the x and y. We have x equals square root of 3y minus 5. Now we have to solve for y. But y is now part of the square root. So we need to get rid of the square root. How do we get rid of the square root? What's the technique? What is the technique we use to get rid of the square root? We square both sides, right? So let's do that. X squared equals square root of 3y minus 5 squared. So x squared equals, the index here is 2 and the power on the outside is 2, so they cancel each other out. On the right we get 3y minus 5, right? Okay. All right. So we're still on our way to solving for y. So the minus 5 and the 3 are preventing y from being isolated. Let's get rid of the negative 5 first. What's the technique we use to do that? The technique we use to do that is simply move it to the other side, right? It was negative 5. When I move it across the equality symbol, it becomes positive 5. Like that. So we're solving for y, which means we need to isolate y. Is y isolated? No. We need to get rid of the 3, right? So how do we do that? We divide both sides. That's the technique, right? Notice the technique to getting rid of the square root, the negative 5, the 3. These are different techniques to get rid of different things. I hope you're catching that. Okay? So here we need to divide both sides by 3. And we end up with y equals x squared plus 5 divided by 3. Are we done? 99% we're done. But 1% remains, right? Which is replace this y with the proper inverse function notation. We started out with f of x, so this will be f inverse of x equals x squared plus 5 divided by 3. Like that. Okay. As usual, I'm always hopeful that your answers agree with the ones that I have on the screen. Okay. All right. Next, they want us to prove that the function f and f inverse, which are given below, are inverses of each other. We know how to do that, right? We've done it. We've done at least 1 or 2 examples so far. Maybe 1 example. So go ahead, do it. You have that one, and then there is a part B to it, that one. But first, go ahead, pause the video, and on your scratch paper, show that these two functions are inverses of each other. Go ahead, do it, and then come back to the video. Okay, I'm assuming you've done that. Now, let's compare our solutions. So, to prove whether or not two functions are inverses of each other, we need to take the composition of functions in both directions and see if in both cases we get x. If we do, then the original functions are inverses of each other. So first, I'm going to take the composition of f and f inverse. Okay, so this means all of f inverse of x gets replaced inside of f, right? As this notation is showing. Where can f inverse go? It can't go inside 5. It can't go inside 4. X is the variable. X is the one term in this whole function that can take different forms. In this case, we wanted to take this form. So we can do that. So 4x minus 5, right? I replaced x with all of f inverse, plus 5 divided by 4. Okay, this is just a neutral sign, plus, and especially it comes after the parentheses. So we can remove the parentheses and say 4x minus 5 plus 5 divided by 4. 5 and minus 5 add up to 0. We get 4x over 4. 4 and 4 cancel out. We get x, right? So there we have it. Are we done? No, we're not done. Remember when we said that to prove that two functions are inverses of each other, we have to take the composition of functions in both directions. We've done this, but we need to do this also to see if we get x. So this would mean we're going to take the composition of the f inverse and f of x function. So this time, function f of x gets replaced inside the inverse function. So all of this gets replaced here. Where can it go? It can't go inside 4 or negative 5. X is the variable. So all of f of x is going to replace x. So we have 4 times, instead of x, all of f, right? Instead of x, all of f of x is replaced x, minus 5. Okay, this can be easily simplified, right? 4 and 4 cancel each other out. This 4 and this 4. We end up with x plus 5 minus 5. Minus 5 and 5 add up to 0. We get x. Okay. So yes, f and f inverse are indeed inverses of each other. Okay? We've shown that. This one, if you haven't done it already, please pause the video, show that these two functions are inverses of each other, then come back to the video. All right, I'm assuming that you've done that. So we have to take the composition in both directions, right? By now you know that. So this time I'm going to put the f inverse inside f. Where can that go? Just x, right? All right, so third root of, instead of x, let's put all of that. X cubed minus 4 and then plus 4. Right? Okay. So what do we have here? Let's remove the parentheses. We've got third root of x cubed minus 4 plus 4. Then we have third root of, minus 4 and 4 add up to 0. We have third root of x cubed. You know, a while back, maybe earlier in this course, we looked at properties of radical expressions, right? Properties of rational exponents. So you can rewrite this as what? As x to 3 over 3 power, right? Any radical expression can be written as some term to some rational exponent. So this is equal to x to first power, right? Or x. So we've shown that the composition of these two functions leads to x, taking the composition function in one direction. Now we got to do it in the other direction. So this time we will take the composition of f inverse of x and f of x. Okay, now this time f goes inside f inverse. Okay, so f, all of this goes inside here. So let's do that. We have square root, third root of, not square root, but third root of x plus 4, put in parentheses, cubed, right? X is gone. Instead, what do we have? We have all of f, right? That's what we're doing. We're taking the composition of function of f inverse and f. And then what else are we left with? Negative 4 on the outside, right? Notice this power on the outside is equal to the index of this root function. So they cancel each other out. They're equal. So we end up with x plus 4, right? Or if you want, I can rewrite it as a rational exponent. So as I said earlier, any radical expression can be written as an expression with a rational exponent. So x plus 4 to third power, and this is the third root, so we can write this as 3 divided by 3, and then minus 4. But 3 divided by 3 is 1, right? So we end up with x plus 4, x plus 4 to first power minus 4, and this is x plus 4 minus 4, and that is equal to x, right? So there, once again, we have shown that f and f inverse are inverses of each other. Okay? All right. So this was all the examples, but I promised you earlier that we would go to the computer to graph all of these and see the relationship between a function and its inverse graphically. Okay, what we've done was numerically. You're now, I think, I'm comfortable that you know how to verify if two functions are inverses of each other, how to find the inverse of a one-to-one function, and the numerical relationship between the two, right? The x and y swap roles. Now, let's compare graphs. So as I switch to the computer, you're going to see a glitch on the screen. Please ignore that. We'll be back. Okay, we're back. Wonderful. Okay, so now let's graph these functions one by one. Okay, so I'll start with number 3. That's where we had the first functions that we calculated for that one, for number 3 on page 2, we proved that those two functions are inverses of each other. And now let's look at them graphically. But we know that they are, graphically speaking, a function and an inverse function are mirror images of each other across the y equals x line, right? So let me, first thing I will do is I will plot the y equals x line. So that's that purple line I just plotted, right? That's the mirror, y equals x line. Now we're going to graph each function and its inverse. And this is number 3 again on page 2. So we have y equals x cubed plus 7. So let me zoom out so we can see this better. So this is that's the original function, f of x. And then inverse function, let's call it z. Let's call the inverse function z. So z equals, and we had x minus 7 to 1/3 power, like that. Do you see it? So this is what we mean when we say that a function and its inverse are mirror images of each other across the y equals x line. Okay, that's clearly shown there. So the red one, the red line, is the inverse function to the graph shown in black. Okay. All right. So I'm not going to erase the y equals x line, but we're going to graph those other functions that we talked about throughout this lesson. So the next one is 7x plus 4. That one, which is a linear function, and I'm going to zoom out so you can see it better, like the blue one, right? And then we found the inverse, and that was x minus 4 divided by 7. Look at that. So once again, the green and the blue line, those two are inverses of each other, and they are mirror image of each other across the purple line, y equals x. Do you see that? Okay. All right, let's graph the next one, function that we saw. Then another function we worked with was y equals 9x divided by x minus 4. Look at that. So we have that. And then we found that's a one-to-one function. And then we found the inverse to be 4x divided by x minus 9. Look at that. Let me zoom out. There. So you can see that the purple line, purple curve, which has two, this is a rational function, so it has two pieces when we graph it, right? So look at the curves, look at the two curves. They intersect right at that point where you have y equals x line. So they're mirror images of each other. Compare that. Assume that y equals x is the mirror. Then the arms of these pieces of each function and its inverse become images of each other across that line. Do you see that? It's just like a reflection, right? The curve is seeing its own reflection across the y equals x line. So this is what it means to find the inverse of a function. Next one was x minus 9 divided by, well, no. Let me put this in parentheses. X minus 9 divided by x plus 9. Okay? So that was the original function. Then we went ahead and found its inverse. The inverse that we found was minus 9 times 1 plus x divided by x minus 1. Look at that. I mean, look at, because this is also a rational function, so it's got two pieces. But look at this piece, this one, when the one that I'm tracing with my cursor on the screen. Look at that and compare it with that one, the red one, right? They are mirror images of each other across this slant line you see, which is y equals x. And then take a look at these two, the red one and the blue one here in the middle. That one and that one also, these two are mirror images of each other across the y equals x line. Do you see it? Okay. All right. So let's graph the other function that we worked on. This was number 7 on page 3. This was one of the square root functions, remember? So we have y equals square root of 3x minus 5. So it graphs like that. And then we found the inverse. The inverse was x squared plus 5. X squared plus 5 divided by 3. So this is, so this is where we have to limit the domain on this one. See, because the inverse function, not the original function is the square root function, which is always 1-to-1. But the inverse is a quadratic function, which is not a 1-to-1 function. It becomes a 1-to-1 function if we restrict the domain to a certain point. So in this case, disregard this point, disregard this portion of the quadratic one is the purple one, the one that looks like a bowl, right? Disregard this piece of it on the left where the domain is negative infinity to 0. So for this quadratic function, which is the inverse function, we need to restrict the domain. I don't know if it'll let me do it or not. It doesn't. Looks like no, it doesn't let me. Maybe. Sometimes it lets you restrict the domain actually here on Desmos, but I don't see it now. Let me back up if I might see it. X squared. No, it doesn't show it to me. Okay. But this is the one case we have to restrict the domain where I was saying earlier. So we need to restrict the domain on the inverse function from 0 to positive infinity. So on the computer, I don't know how to do it. Let me see if this will let me do it. Let's see. No, convert to table, duplicate, no. Let's see if that, no, that would not be. It's not what I want. Sometimes when you enter these functions, it'll allow you to set the domain, but this one it's not letting me do it. But the inverse function is a quadratic function, and we need to restrict its domain to 0 to infinity. That way, you can see that this piece, the green one, which is the square root function, and the purple segment, which starts from 0 and goes to positive infinity, is the mirror image. But this one on the left should be left off the domain. On paper, we could easily do it, but on the screen, I'm not seeing how I could delete it. Okay. All right, so let's look at another one of these functions we worked on. These are on page 4. these are the ones that for which we verified that they are inverses of each other. So one of them was x plus 5. This was the original function. X plus 5 divided by 4. Okay. Let me zoom out. Or maybe I should zoom in, actually. Yeah, that's a linear function, so it makes sense. And actually, I should zoom in, not zoom out. I had zoomed out too much, actually. Okay, so that is the green one. The purple one is the y equals x, right? So let me, the purple one is our mirror, y equals x line. So the inverse of it, which we verified, was 4x minus 5. Right there. So notice at this juncture, where they intersect each other, is right there at the mirror. And the green line has its mirror image across the y equals x line on this side, Okay? In this case, they're both, the mirror and 4x minus 5 are graphed as, both of them are purple. They shouldn't be. The program should graph them in different colors, but this time it didn't. Okay, the last one, again, these two were the ones for which we verified that they're inverses of each other. This is part B on page 4 of the worksheet we just did. So the original function was the third root of x plus 4, which is x plus 4 raised to 1/3 power, right? Any radical expression can be written as a rational exponent, so that's that, right? That's the graph of that, the original function, which was, let's call it y here, equals, like that. And then z is the inverse function, and that was x cubed minus 4. Look at that, right? So you can see here, and maybe we can zoom in even more. Yeah, this is even better. So the black curve has its mirror image in the red curve across the y equals x line, which you see in purple, right? The black and the red curve are the inverses of each other, inverse functions of each other. So you can see them being mirror images of each other across y equals x line. Okay? All right. So we have come to the conclusion of another lesson here, 5.1. And I thank you for persisting through this video all the way to the end. So for now, have a very nice day, and I'll see you again next time.